Hello and welcome to lesson 5 of chemistry, the atoms and periodic table topic, and cunningly called, just choose a pen, isotopes. And obviously it's called that because it's about isotopes. So where have we been? We've been looking at early models of the atom and then becoming better models of the atom, and actually now the modern atom, and we had a lesson on that. The modern atom, a little nucleus with all the mass in it and electrons in shells around the outside. From here we looked more detail at what's inside an atom, so these electrons being negatively charged and the nucleus of the atom containing the protons and the neutrons. And then last lesson we started looking at, about the same time as Dalton had come up with the atom idea, and then Thomson had done this, and then before Rutherford's time we had a scientist trying to put them, John Newlands tried to put all the atoms into a table, and then Mendeleev improved it, and now we've got the modern periodic table. So when we look at an atom on the modern periodic table, it has two numbers next to it, so let's not choose the same one as last lesson. Let's choose oxygen. So there's my oxygen nucleus. Around the outside it has 8 electrons. This shell could only fit 2 in it. And this shell, it had 8. Ooh. 1, 2, 3, 4, 5, 6. Oh no. 1, 2, 3, 4, 5, 6, 7, 8. That's it done. And that's because on the periodic table it looks like an O. There's 16 and an 8. And what that tells me is, this is how I draw the electron structure. What's in the center? Well, there's the atomic number. There's 8 protons. And 16, take away those 8. In this case, it equals 8 as well for my 8 neutrons with a neutral charge. So 8 protons, 8 neutrons, and here 8 electrons in shells. And where would that be on the periodic table? Well, periodic table had groups 1, 2, then a gap, 3, 4, 5, 6, 7, 0, and that would be here. It would be in group 6, purely because there are 6 electrons on the outside shell. Oh, I've drawn an extra electron. Need to get rid of that. See if I can find a rubber. Oh. The OCD in me makes me have to go back and draw that back in. That's better. So it's over here in group 6. Have a look on your copy of the periodic table quickly, please, and just find oxygen, and you'll see it there. And next to it there'd be fluorine, which has a 9, and before it there'd be a 7. Ooh, 7 is nitrogen. 9 is fluorine, purely based upon how many protons they have, and they go in that order. So, quick questions. I will allow you, I think you need to pause for 3 minutes, and remember what we're doing. We're writing the question, then we're writing the answer. If you're unsure of the answer, maybe write it in pencil so you can correct it afterwards. But either way, when you look back on it, if you've made a mistake, that's great for your learning in the future, because you'll realise you didn't know it first time round. Okay, pause now, and then when you're ready, we'll go through the answers. Okay, hopefully you've unpaused. Answers. If the plum pudding model were true, what would have been the outcome of Rutherford's? So Rutherford did an experiment. He has gold atoms, very thin gold leaf. He fired little alpha... Oh, no, that doesn't work. He fired little alpha particles at it, and if he'd been true, it would have just gone straight through, because the mass was so spread out. There would have been no problem at all. That's not what happened, but that's what would have happened if it was true. So if it had been plum puddings, the charge was all spread out, therefore they would all have gone straight through. What did Chadwick discover? Chadwick's the guy who discovered, if you put neutrons, you have it correct. The periodic table from last lesson is organised into periods, and those are the rows, and groups, and those are the columns. And if an atom has 7 protons, what's its atomic number? Well, the answer is 7, because the atomic number tells us the number of protons. And just one question there, going back to biology from a while ago. What process occurs in the mitochondria? So what are mitochondria for? And the answer, I'll put the spelling so you get it correct. Respiration. So you remember, hopefully, things like muscle cells have loads of mitochondria, and other cells like skin and fat cells, etc., don't have many mitochondria, because respiration is about energy. Okay, there's the answers anyway, just in case you want to check that I've told you the right answers. So hopefully you've marked your own and corrected them, paused when you needed to, and if I got any wrong in the answers I've given you, then you can sack me. Thank you. Right, this is where we got to last lesson. Groups being similar to each other down a group, and periods going across and filling up shells. So, for example, here I have lithium. It has 3 electrons. I fit 2 in the first shell and I fit 1 in the next. And look at it, it's in group 1. Well, that's a coincidence. It's got 1 and it's in 1. Beryllium has 4 electrons. Let's try and draw that out. Now, you notice that I'm doing it slightly differently to normal. Normally what I'd have done is I'd have gone lithium, 1, 2, and then 1. So drawing this is the electron structure, and drawing this is the electron structure, 2.1. However, this one's a lot faster for me to just go over this. So beryllium has 4, 2 in the first shell, 2 in the second, 2 in the outside shell. What group is it in? It's in group 2. Let's just see if this continues, because I'm quite amazed. Ooh. Boron. Let's go up here and do it. 2 in the first shell, and you guessed it, 3 in the next shell, and it's in group 3. Ooh, 2 in the first shell for carbon, 4 in the next, and it's in group 4. Oh my. So what we're doing here across the period is we're filling up that shell. So it goes 2 and then 3, 2 and then 4, 2 and then 5, etc., etc. And this end one has 2 and then 8, so the shell is full. Come back to why it's called group 0 another time. So, does the pattern continue? Let's look down here. Right, 13. 13, so the first shell held, let's do that at the top. The first shell could hold a maximum of 2, then it was 8, then it was 8, and then it was 18. And that's what we should have learned, I think, in lesson 3. Yeah, it was lesson 2 at the end and lesson 3. So now let's do it for aluminium with 13. So it's got 2 to fill up the first shell, and then I use 8 filling up the next shell. That's 10. And then I go to, oh, there's 3 left over. 3. Yeah, that's got 3 on the outside, and it's in group 3. So the pattern goes down. They've all got 3 in the outside down this group, and that's why they behave in a similar way. These don't behave similarly to each other because they have different numbers on the outside. Right. So what is an isotope? And the answer to your question is that can't be true. Look at that. I know what you're saying to yourself is look at what? And I'm saying, I'm just getting my highlighter. Look at chlorine. just colouring it in now. Why? Because colouring's therapeutic. So there I am with my chlorine, and it's got an atomic mass of 35.5. But that can't be true. You can't have half a neutron or half a proton, and that's because it's an average. Now, what I just wanted to quickly do is try and explain what an isotope is. We're going to come back to chlorine in a few minutes, but here's an easy example. When they find some hydrogens, hydrogen has one proton in the middle, and according to those numbers on it, it has one electron around the outside. So in the nucleus, there's just one proton here, one positive charge, and one electron negative charge around the outside. And that's hydrogen on the periodic table. And 99% of hydrogens are like that, but we do find some of these. A proton and a neutron, and because it's got one proton, it's got its one electron. So it's very similar to my first diagram, but now I'm going to draw this. Now, because it has one proton, it is hydrogen. So here it is. It has one proton, the atomic number. But what's the mass now? There's one proton and one neutron. 1 and 1 makes 2. Quick math in it. What? This is hydrogen. That's crazy. That's hydrogen. That's hydrogen. They're both hydrogen. Why are they hydrogen? Because they have one proton each. But this one is like a slightly heavier hydrogen because it's got a neutron. That's what the word isotope means. Isotope. Isotope means atoms of the same element, because this is a periodic table of the elements. The elements are all these different atoms that exist. Atoms of the same element with different masses. Just going to give you one more example while we're here, and if you're thinking about that, I would pause and take time to write down what isotopes are, and to do this as a worked example for the fact that hydrogen, there's that hydrogen, there's that hydrogen. They just look different because of this little particle, that extra neutron. I'm going to change colour again because I confused myself. I'm going to go up here. Carbon has 2 naturally occurring isotopes. I can use the word now because we know what it means. Isotopes, just different types of the same atom, different masses. Here is carbon, it has 6 protons. Here is carbon, it has 6 protons. Here is our normal everyday carbon. How many neutrons does it have? Well, 6 of them are protons and it weighs 12, so the other 6 must be neutrons. And here is a different. This is called carbon-14. It's a radioactive element. It's used to help in radioactive dating. It's naturally occurring. So, for all the carbons out there in the world, most of them are like this. Normal carbon, here you go, on the periodic table, that's its normal one. A few are like this. They are the other isotope of carbon, the heavier version with the neutrons. Okay, now hopefully you've paused and you've done a couple of examples. Deliberately, this is here, just to check so that my scribbles don't end up as your recorded bookwork when you could make it better. If 2 atoms, they have the same number of protons, just like those carbons and hydrogens a minute ago, they are the same element. However, if they have the same number of protons and they have different numbers of neutrons, they are called isotopes. So here, for example, this is protium, is the normal everyday isotope of hydrogen. Deuterium is that isotope of hydrogen I just drew with the extra neutron here. And there's even a third isotope of hydrogen, which has a mass of 3 in the centre. It's still only got 1 proton, still only got 1 electron, but tritium. Tritium is the third isotope of hydrogen. Now, go back to my normal pen. Don't try remembering boring chemists. Dalton, Thomson, Rutherford, Bohr, Chadwick. He discovered the neutron. That's all we know about him so far. It was his discovery that allowed us to explain why isotopes were different. So we knew about isotopes before him, but we didn't have a clue what was causing these differences. Why did we have a heavy carbon and a light carbon? And now, because of Chadwick, we knew that actually, there's 2 isotopes of carbon, that carbon-12 and carbon-14. So that's how Chadwick's work helped us. Okay, so here's our normal chlorine. And there's our naughty chlorine. Not naughty, just a different isotope. 18 neutrons, 20 neutrons. Same number of protons, otherwise there would be a different element. Different numbers of neutrons. And they're called isotopes because they have the same number of protons and different numbers of neutrons. Pause and write that down as your example, please. Then unpause. Chlorine 35, there are more of them, 3/4. So if you look on here, there's one of them and one of them, and there's 3 out of 4 on here. These have a mass of 37. However, this has a mass of 35, 35, and 35. So when we work out the mass of chlorine as a whole, it has 17 down here for its number. What do I put as the mass number? Now, some people often guess and say, well, it's 36. 36 is good. I like 36 because like one's 35 and one's 37. And it's like halfway between. That would be fine if half of them were like this and half like this, but it's not. 3/4 are like this, there, and only 1/4 is here. So it's going to be closer to 35 than it is to 37, and it's not going to be halfway in between. Now, as I just said, if you're doing the foundation paper in science, and hopefully by now in year 10 you've got a good idea of whether you've been doing foundation or higher. If you're doing the foundation paper, that's absolutely fine. Make sure your notes are finished off. Take a photo of your work, go to Google Classroom and please submit it to me, and then I'll get back to you on that. If you're doing higher, carry on for another couple of minutes. To take an average of them, you, for example here, 35 and 37 and 37 and 37. Now, that's easy for chlorine, and that's why the average comes out when you divide it by 4 at 35.5. However, what you need to do in this last couple of minutes is this is how you work it out for any element. So based upon the example we just did, we said there is 75% of, what was it? It was the one with 35. The mass was 35. So you do 75 times 35. There's the sum down here. And then you add it to 25% of that heavier one of chlorine. 25% of, and what was the mass? Oh yes, 37, because I can see it in my notes from earlier this lesson. That's what you're thinking to yourself. And that goes in there. And because the percentages, we divide it by 100. So the answer, 35.5, what's on the periodic table. And because of a bid mass, you will do that sum in brackets first, then you'll do that sum in brackets. There's no indices. Then you'll add them together, and then you'll do the dividing, and then you'd get that answer. I think you should try that on your calculator. So we'll do some examples of these in future lessons, but for now, you've got the equation, you've got this one down as a sample. Well done. Take a photo of your work, send it in, and we'll see you next lesson. Hopefully you can make the live lesson.